Okay, we are recording the class, and let me start to share my screen with you all. Just a minute. Okay. Yeah. My internet connection today is not so good, so if you have some problems to see my screen or to hear my voice, please just raise your hand, okay?
Okay.
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 In the last class, we finished our class discussing how could we measure changes of the relief topographic changes in soil. And we discussed that the transition between horizons is very important because especially the surface horizons, they are always formed in a parallel condition to the surface. So if you can see some changes of inclination of this organic and surface horizon, this means that we could measure some topographic variation of the horizon and soil profile. Okay. We also discussed about water table changes, and we discussed that the spodic horizon, the B-spodic horizon, is a horizon that's very important because it is formed in the water table. It tells us where the water table was or is, depending on the condition of that soil. Okay, so if we could describe a soil with different spodic horizons, like here it's a horizon, an E horizon, and here we have a B, a spodic horizon here, and now we have an A horizon, and again we have another B horizon, a spodic, again a spodic horizon. Okay, I could date this horizon and I could date this horizon too, and I can measure. I know when the water table level was here in the past, and in the second condition, and maybe I can measure other spodic horizons in the subsurface in deeper conditions and age that are more close to the modern age. Okay. Other soil property that could help us a lot to understand and to measure changes of relief is the presence of terry crusts and salts in a specific horizon or in the soil. Okay, salts, they are formed especially in the surface horizon. So if you are describing a paleosol and you describe something like A horizon and a B horizon and P1, P2, P3, and you found here a new horizon that present a lot of salt, a high content of salts, a high pH, and several salts like gypsum, calcium carbonate, and magnesium carbonate, and other sodium chloride and other salts. This suggests to you that this is a ancient or old surface horizon that was buried. Okay, because salts, they are formed in dry conditions in semi-arid or arid conditions, and they usually are formed in surface horizons. And why we can understand that? Because
Teacher,
yes,
the presence of the dairy crust and salt in profile explain about the climate conditions. That's okay?
yes, they could represent us very much the variation of relief or climate conditions, yes, because they show us that something happened in that soil. Okay,
The position of
just
the position of the crusts and salts uh, uh, always in the lower in the profile the the minha pergunta é tipo assim, todas as vezes que a gente encontrar a Dirty Crust e os saltos, a gente vai estar sempre falando que eles vão correr nas partes baixas, mais baixas do perfil? É isso?
oh no. Amanda asked if we always could find the crushes and salts in subsurface horizons. Is it? And it's not exactly this, Amanda, because we have some chains, okay?
Okay.
Let me explain you.
Okay.
For example, this is a modern soil, okay? So this is the surface. You can see here some shrubs or grass, something like that, okay? And this soil is under a dry climate, so it's a semi-arid or even a arid climate. So you have a low rainfall, but a high evapotranspiration. And this soil, it's not so deep. So you can find the rocks here. And it could be granite or gneiss, something like that, or even shale is not a problem. And when rains, the water penetrates the soil and stop to infiltrate when this water finds a low porosity layer like the R layer here. So water start to accumulate in this region, and water start to dissolve, to destroy the primary minerals. So feldspar, plagioclase, and other, the biotite, muscovite, on other primary minerals start to be destroyed, and they release some elements, some chemical elements, okay, like potassium, calcium, chloride, magnesium, and other elements, okay? So we can see here in this layer and on our water layer that's rich in some elements, okay? Elements that could be released from the weathering of primary minerals. In this dry condition, in this arid or semi-arid weather, the climate, you can see that in the dry season, the water start to move to the surface because you have a high incidence of solar light here. So the temperature here is very high, and the soil start to get dry. And by the difference of potential, the water start to move to the surface, from the subsurface horizon to the surface. And when water migrates in the direction of the surface horizon, water start to evaporate because the temperature is high. And when water is close to the surface of the soil, this temperature is highest in the soil profile. So you can see that water evaporates, especially in the surface horizon. So water is released from the soil, especially in the closest horizon to the surface, in the surface horizon. And in this condition, all these elements that were in water start to precipitate as salts. So we start to precipitate some chloride, potassium, sodium chloride, and other salts, calcium carbonate, magnesium carbonate, and other salts. They start to precipitate in the surface horizon. They could be precipitated inside into the soil in the subsurface horizons, but the highest content of salts you can found in the surface. So if you found a paleosol, an ancient salt, that presents a layer or a horizon with a lot of salts in the subsurface, this could suggest this could be a buried surface horizon. So in the past, this could be the surface horizon that present a lot of salts because it was formed in a dry condition, but the erosion and sedimentation of material produced a new soil that overlaying all these horizons. And now I have a new horizons here, and this salt or this salt-rich horizon was buried. Okay, this is an evidence that suggests you that, okay, I have a buried horizon, I have a buried soil. And now I can see this A, C1, C2, C3, and now I have a 2A, B, a buried A horizon. Okay, so the presence of salts, they generally are abundant, the higher contents are in the surface horizon, and if you can see a buried salty layer, this could represent, of course, could represent, is not always, the could represent a buried surface horizon, okay? Because salts are more abundant, they are more relevant in the surface horizon because they are precipitated in the surface horizon because the higher temperatures. And of course, if you can see a horizon that presents a lot of salt, you can indicate that, okay, this surface horizon was formed in dry conditions, and maybe these horizons that are above, that overlying this horizon, they was formed in wet conditions. So I can find here a lot of kaolinite, goethite, hematite, gibbsite, other minerals that was formed in wet conditions. And here I found a horizon or even several horizons that was formed in dry conditions because we can register the presence of salts. Okay? The dirt crusts are different. They are not only formed in the surface, depend on the kind of dirt crust that you are talking about. You can find something like fairy crusts or fairy crat. Oh, sorry. Fairy crust or fairy crat. Depend if you are French or you're talking Portuguese or English, okay? You can find some silicone crust or silicone crust. You can also find magnesium, even with organic matter. You can also find aluminum, gypsite crusts, okay? And iron, silicon, magnesium, organic matter, aluminum, manganese. It's not so common, but you can find some. And of course, calcium carbonate and other carbonate dairy crusts. So we have several crusts that are very hard to break it, okay? And depending on the nature of this dairy crust, they could be formed in surface or in the subsurface horizons, okay? Silicon, iron, aluminum, and manganese, in organic matter, they generally are formed in subsurface horizons. So iron, aluminum, organic matter, silicon, and manganese, they generally are formed in subsurface horizons. So they generally are formed in subsurface horizons because they depend on the high weathering and concentration of these elements in a specific layer. Sometimes they need a change of pH or EH, okay? Like the silicon. Silicon, it's very interesting because you only can see a dairy crust that's composed by silicon if you have a horizon, surface horizon, like here. You have a high pH, and this high pH destroy the silica and the minerals, the primary minerals. So feldspars, plagioclars, olivine, pyroxene, they are being destroyed and they release silica. And the silicon start to concentrate in a horizon which present a low porosity or a low pH. A low pH induces the precipitation of silicon and the voids of this horizon and induce the cementation of this horizon or this layer and create a cemented horizon, a dirt crust. So dirt crusts that are composed especially by silicon, they need a change of pH from high pH to low pH or high porosity layers to low porosity layers, okay? It's why it's so common to find some dirt crusts that are composed by silicon in dry areas, because these dry areas present a surface horizon that has a high pH, something like 6.8 or even 7.2 or even higher, like 8.6. This high pH induce the destroying of the primary minerals and induce the leaching of silicon, okay? And the low pH couldn't help the release of silicon. They induce the precipitation of silicon as secondary minerals, okay? So the voids start to be fulfilled by silicon, amorphous silicon, okay? So the presence of these dirt crusts they could show us some change of climate conditions and some change of relief if you are looking for its position. Like if you found on piezoplint surface, if you found a horizon or a layer that is a terry crust or a fairy crust in the surface, okay, I found a layer or horizon that's cemented by iron. I know that this condition is not formed in the surface, only on the subsurface horizon. So all the horizons that should be above, that should overlie this horizon, this iron crust, was just eroded and lost. So now I can found this iron crust in the surface because the overlying horizons and layers were eroded. Okay, so I can register a change of relief. Okay, it's very common to find these conditions because these terry crusts, these cemented layers, they are highly resistant to weathering and erosion, and the materials that were above, they could be easily eroded in comparison with this cemented layers or horizons. Okay, so it's quite common to find some of these iron crusts or silicon crusts or cemented crusts in the surface, but they are not formed in the surface. They were formed in subsurfaces, and now they are exposed by erosion. Okay?
Okay, teacher. In Brazil, it is common to study the fairy cracks and association with the the change of the conditional climate.
Yeah. In the tropics, we can find several manuscripts, articles, books about these terry crusts and especially the iron crusts, the ferricrete, as you said, because the weathering helps a lot to produce this kind of iron cemented layers.
Yes.
Mhm.
Okay.
Okay. Oh, I'm sorry. And the last option is one that we said in the last class is to use some measurements, some techniques in the lab to measure this change of relief. Okay, so we can use the OSL to measure some change. This is a technique that could show us the burial age of a material. We'll discuss this technique in the next classes, but if I have some fluvial soil that presents several layers, like I can find here a horizon at C1, C2, C3, C4, C5, and blah, blah, blah. And every sea horizon have a specific properties, like these are sandy, clayey, siltic, sandy, clayey, and etc. I can register, I can measure the age of the sedimentation from each horizon. So if I collect a sample in this horizon and analyze using the OSL technique, I can measure, I can have an age of the burial sedimentation process. I can measure when this C5 layer was buried. Okay, not was formed, but was buried. Okay, so it's quite important if you are studying chains of the geomorphological landscape, if you are measuring some erosions and other properties, could be very useful. Okay, and of course I can collect several samples and I can know now how is the rate of the sedimentation in this area. If I compare the thickness of these layers and the age of each one. So, okay, the difference of age here, it's something like 10,000 of years. Here's just 8. Here's 2. And here it's 1, and here's just 200 of years. I can see that there are a huge gap here, and this huge gap maybe suggests an erosional process between the sedimentation of these two layers. So at 8,000 of years before the present, this layer was buried by a layer that was almost completely eroded, and only at 2,000 of years before the present, this layer was buried, and only 1,000 of years. So this change of magnitude of the values, especially here, show us an erosional phase between these two layers, these two horizons. It's quite important to us to understand that it's not only sedimentation that the soil profile suggests and show us, but an erosional phase between these two layers can be described too. We will discuss about this in the next classes, okay? It's just to understand that we can use this technique very well to understand the evolution of the landscape, especially if you are studying terraces and alluvial plains or marine terrains or colluvium. If you are studying the relation between soil and geomorphology evolution, this technique could be very useful. And it's a cheap technique. It's a very cheap technique comparing to some other dating methods, okay? Especially if you are comparing to beryllium and aluminum dating. We can isotopic fraction these elements, and we can measure the rate of erosion and the rate of sedimentation in a specific soil profile. We collect systematic samples at every 5 or 10 centimeters and measure the content of beryllium or aluminum. Oh, it's not 26, it's only 25, I'm sorry. We can measure these quantities and the isotopic fraction of these elements, of these isotopes, and this could help us to understand how much and how long was the sedimentation and erosional process to form this soil or this sedimentary pack. Okay, we'll discuss about this technique too. It's a very good technique, but it's very expensive too. So we usually don't find several studies using this technique because it's very expensive. But it's very useful, especially if you are trying to achieve older periods of time, like the OSL it achieved the beginning of Cenozoic, but the beryllium and aluminum could achieve even the Mesozoic ages. So we can measure and we can understand the formation of ancient soils if we use this technique comparing to OSL. Okay, and of course they both are better than isotopic carbon because it's just 50,000 of years, and this is more than 500,000 of years. Okay.
I remember. Oh my god. I remember this analysis of topic fractionation of the beryllium and the aluminum. In Brazil, don't have conditions for to release this analysis. Always put the samples for to to uh, to get this analysis in other countries. Okay.
Yeah. I'm not sure about this, but I've never seen a study that was conducted completely in Brazil that made this analysis. As you said, in general, they send the samples for abroad, like France or England or United States, and they measure these elements, these isotopes in other countries.
Yes.
We have the equipment to do that, but I
Yeah.
think that to measure these isotopes are not so easy, and the preparation of the sample, it's not so easy too.
Yes.
So it's why I think that they generally analyze this broad, because the preparation is quite hard. We'll discuss about this in the next classes. The preparation of the sample, it's hard, it's quite difficult, and it's quite expensive too.
I think in Brazil only this part of to clean the samples, only this part, but the other
Maybe.
uh, um, etapas, um, we it is necessary to
To send
to
the samples.
yes to send the samples for other countries. I can
Yeah.
see I think it's Swiss and
Oh,
Dinamarca,
Switzerland.
Denmark.
Mm-hmm. Yes,
Yeah.
several labs in Europe, they produce this analysis, they done this analysis, but as you said, if you send a sample
Mhm.
that was prepared in the Brazil, so it's cheaper, but it's not so cheap. It's too
Yes,
expensive. It's too expensive.
yes, yes.
And now we'll discuss about the last soil formation factor, that's time. It's quite important to us in this course to discuss how time influences the soil formation. Although generally we don't use the soil formation factor in the study of the soil. You can look several articles that even mention when soil start to form or when vegetation cover, the modern vegetation cover start to grow in that area, or when we can register modern climate conditions in that area. So you can easily find several articles that only ignore, find articles that at least mention time as a soil formation factor during the writing of the article. Okay, so it's soil formation factor that we usually and intentionally forget to consider because it's expensive to include the soil formation factor in the analysis, because we should produce a lot of data and specific samples to make this analysis. And in general, the soil formation schools, they don't have the equipments to make this analysis. So it's expensive. So we intentionally forget to consider this soil formation factor. But it's quite important to us to understand how much time does soil need formation. Of course, this depends on the kind of soil, the soil order or the soil group, and which process it's acting or act in the past in that soil, and how the other soil formation factors could interact. If you think that you have a dry climate conditions, maybe organisms are not so intensively and deeply acting in the soil formation. But if you have a wet climate, if you have a wet condition, maybe the organisms, they intensively create soil by bioturbation or other process. So of course, time isn't relative, because depends, of course, of other soil formation factors too. And if you have a parent material that have higher content of clay or a lower content of clay, if the parent material is a felsic rock or mafic rock, of course, all the soil formation process will be different, and they span different times, of course. But it's quite important to understand how much time they need to produce soil, okay? It's quite interesting that some process could act in a fraction of days. So days or weeks could be enough to formation of a specific horizon. So the glaciation process, clay properties or a clay horizon or a spodic horizon could be formed only for some weeks or days, because these processes are very fast. So the migration of organic matter in a sandy soil, or the reducing of iron and the formation of gray horizon or gray layer with only iron 2 could use only some days or weeks, okay? We can also find some process that needs some hundreds of years, like the melanization, formation of horizon that present a dark color because organic matter, it's being decomposed. So the formation of a horizon needs some hundreds of years, okay? It's not so fast like the formation of a C or B horizon, a clay horizon, or spodic horizon, okay? And we have some processes that, of course, they span millions of years, like ferralization or plintization, formation of concretions, iron concretions or iron nodules. They spend too much time to us, so we can't see that in the field, but we can measure and describe this evolution using morphological and chemical and physical studies or analysis of these layers and horizons. Okay. So it's quite important to us to understand that the formation of horizons, diagnostic properties, diagnostic materials that we use to classify soil and that we use to understand how soil evolve during time, through time. They spend different intervals, they span different times. Okay, the timing of each process is different by itself. Okay. For example, we can see here a calcium horizon that presents a lot of calcium carbonate. It's this, like this, and this condition represent a cemented layer of calcium carbonate here. But to form this kind of horizon or layer, we could see in the beginning soil with no models or no calcium carbonate precipitated. And we can see in a fraction of hundreds of years and thousands of years, we can see formation of discrete models, and they could evolve some discrete bodies that could be concretions or nodules of calcium carbonate, and then they could evolve to a thin layer of calcium carbonate that is discrete in the soil profile by the amalgamation, the union of all these concretions or nodule, and in a fraction of thousands of millions of years, we can see a very thick layer of calcium carbonate concretions. So the process spent a lot of time, millions of times to form, to create this specific horizon, a horizon that's cemented by calcium carbonate. And the process starts with creation of some models. After that, some nodules or concretions. And after that, we can see both. We can see models and we can see some layers or some horizons that get thicker with time. Okay. This is quite interesting because we can see all these conditions in the field. And if you are studying an area, maybe you can see different soils in different stages. So you can understand that, okay, I have some soil that presents thick calcic horizon. Some soils present only concretions and nodules. Some soil profiles present only models, and some soils did present anything. We only can see the limestone here, but we can't see anything inside the soil, inside the A or B or even the C horizon. So we can measure that these soils probably have different ages. Okay?
Teacher, only the calcic horizon is in the figure 5, or in all the profiles have a calcic horizon?
Could you repeat, please?
Calcic horizon occur only the 5 profile, or in all profiles have a calcic horizon?
Okay, I understand now. Yes, the calcic horizon, you only can identify here and here. And if the content of these nodules or concretions is high, we can also found it here. Okay, but here and here, no. We can't found. You can see here the example. Here it's just a B horizon with some models, okay? And from here to here, you already present the calcic horizon. But of course,
Okay.
here it's a calcic horizon that's formed only by concretions or dials. Here we have the both, and here we essentially found a cemented horizon. Okay?
Okay, and the presence of the calcic horizon is important for to measure about the time, the formation, the profile, okay?
Yeah, and you can see the vegetation here. It's a typical vegetation from dry areas. So you
Okay.
can understand the age of this material, and you should remember, okay, if I have the precipitation of calcium carbonate, they are related to a dry climate. And if I found a cemented horizon, a calcic horizon that's thicker, probably this dry season was very stable for time. So this
Okay.
region was submitted to a dry climate for a long time. Okay?
Mm-hmm. Okay, teacher.
You can't you can form this horizon very quickly, like just 100 years. No, it's not enough. You need that area suffer a dry climate, was submitted to a dry climate, a dry conditions for a long time to form this
Okay.
horizon.
And is usual use the sample with a calcic horizon for to dates in OSL?
No OLS. No, the
Mm,
OSL, they generally don't use, but you can use, in this case, carbon,
okay.
okay? Depending, of course, of the age of this carbon, but you can measure the isotopic composition of these materials, and you can differentiate this precipitations from the rock, from the parent material, and you can date this material using carbon, the isotopic carbon.
Okay.
If the material is very old, or is older than 50,000 of years, so you can use other elements or other methods to date this material, like
Okay.
some potassium argonium math, some uranium and thorium math. So you can use other maths to date this material if this material is older than 50,000 of years before the present. Okay?
Okay, teacher. Thanks.
Okay. So in the first case, try to date this material using isotopic carbon math, and if you couldn't date, so try another math. Try math that could achieve an older age.
Professor,
Yes?
a doubt about the formation of the cemented horizon, this calcic horizon. The cementation is occurred through the dissolution of these concretions, or because of the just the accumulation. How this happen?
Okay, Johanna. You can have both processes, but in general, they are related to a high concentration of calcium and carbon dissolved in the water. So they start to precipitate in the voids, okay, and they get larger and larger, like a nodule or a concretion in these cases. And if you present a high content of calcium and carbon in this layers, they start to get together, they start to coalesce, they start to get the union, they start to be a continuous layer, okay? Because you have a high concentration of calcium and carbon in the voids, in the pores, okay?
Okay, I got it. Thanks.
Okay, welcome. Of course, the calcium carbonate accumulation depends on the weather. So if you have a weather climate, you can't accumulate very rates, a high rate of calcium carbonate. But if you have a lower precipitation, like both are dry climates, but of course this is drier, so you can take a higher concentration of calcium carbonate, and of course this process of a formation of a calcic horizon will be faster in a drier condition than this wetter condition. So the time, of course, affect the formation of a calcic horizon. How much it's dry, the climate will be faster the formation of a calcic horizon, okay? And again, of course, we also should understand that in past, the concentration, the pressure of dioxide of carbon, it's higher or could be higher or could be very higher than today in the soil and of course in the atmosphere. And these both pressures influence the formation of calcium carbonate in soil. So if you are dating very ancient soils, maybe you should consider that this pressure could be different in the past from soil and from atmosphere, okay?
Teacher, low presence of the CaCO3 is explained about the process of the dissolution, okay?
Oh, yes, but especially the precipitation, because to precipitate calcium carbonate, you need a drier condition. Think,
Okay.
if you have a soil, and you have limestone here, and this limestone is getting weathering because water penetrates in soil, and water are destroying the primary calcite here, the primary calcium carbonate, and you produce again a water with a high content of calcium and magnesium and several elements, but you are in a dry climate, so the evapotranspiration is high, the temperature in the soil surface is high, so water start to migrate by the voids from the subsurface horizon to the surface horizon. And during this uplifting of the water, the calcium carbonate could be precipitated because water start to be released by evapotranspiration. So the evaporation of water increase the concentration of the calcium carbonate in the water, so you start to precipitate the calcite in the soil. And how much drier is the weather, how much drier is the climate, how less content of water you have in soil, faster and higher content of calcium carbonate will be precipitated here, okay?
Okay, teacher.
Okay, so it's not only about the solution, but especially the precipitation of these materials, okay? Drier conditions induce higher concentrations or higher contents, or favor the precipitation, not the dissolution, but the precipitation. And this climate, this wetter climate, also favor the precipitation of calcium carbonate, but it's not so easy because it's too wet. Okay?
Okay, teacher.
Okay. Of course, we are talking about climates that are very dry, but when you found a driest climate like a desert, you can find something like this. You can find a high accumulation rate of salts. Okay. Other processes that don't need the precipitation of something, but the migration of clay, for example, the clay alluviation, could expand some millions of years too. So if we begin with a soil that presents several layers of clay and sand, the migration of clay and the formation of a horizon that present higher content of clay in the subsurface horizon compared to the surface horizon, and a horizon that present beyond higher content of clay, some clay skins, because clay migrate from the surface horizon. The low clay content that we can present here are clay skins in the surface of these aggregates, these pads. You can spend something like some hundreds of years, 10,000s of years, or even some millions of years to produce an argillic horizon, a horizon that's formed by clay skins and higher content of clay in the subsurface horizon. So it's not so fast again, but we can easily see some little differentiation with just some hundreds or 1,000 of years, but we need a lot of time to produce an argic horizon that is very thick. And again, we need to understand that if I found some profiles in the field like this conditions that present thick, a deep horizon, or deep argic horizon, so indicate to us that this soil present a very old condition, a very old formation, when a stable climate condition. You can see by the vegetation here that indicate to us a wet condition. So this area, this study area, was submitted to a wet climate condition for a long time. So the clay alluviation spends a lot of time, so needs climatic stability. So you only can form an argillic horizon, an acrosol, a nucleosol, an argisol, if you present climatic stability for a long time, because the migration of clay, the formation of a horizon that present a higher content of clay in the subsurface and present clay skins spend a lot of time, spend thousands and millions of years. Okay? Okay?
Yes, okay.
Okay, teacher. Okay, teacher.
Okay. And of course, weather also influence this process. If you present drier conditions, you spend more time to produce an argic horizon. so to produce clay skins and a higher content of clay in subsurface in dry conditions like the Brazilian semi-arid or another semi-arid or dry area, you need more time, at least 1.5 more time than in wet conditions. So if you found a soil that presents an energetic horizon and it was formed during all the time in dry climate, of course you are watching, you are looking at a very old soil because it spent more time than in wet conditions. But every time we should avoid make a mistake or mix what are stress features and what are clay skins. We can discuss this in the next classes, okay? So we need to try to avoid mix this and avoid to classify an energetic horizon as an energetic horizon, something that's not present clay skins, okay? The parent material also influence the formation of our angelic horizon. You can find easily our angelic horizon if you present clay-rich materials. So if you are looking at a horizon that was formed from the weathering of a mafic rock or clay alluvium, of course, could be easier and faster to produce that angelic horizon. But you found some material that's formed on felsic rock, like a granite, or it's formed in a siltic alluvium or sandic alluvium, a material that you don't produce or you don't have a lot of clay, you spend more time to produce an energetic horizon. Okay. Other processes, the littering and paludization, that are processes related to accumulation of organic matter in the surface and produce an organic horizon that we can call O or H, depending on the system that we are using. Soil taxonomy only use O, and WRB and Brazilian soil classification system, they use O and H symbols. The littering and paludization. What?
No, I remember I learning this process, littering and polarization, in my master degree. In the histosol, we was studying. We found three kind of the horizon. No, the kind of material. Sapric, amic, and oh my god, I don't remember. But it's very interesting, this process in histosol.
Yes. Yeah. It's very useful to study this kind of horizons because they are very large deposits of information, so we can understand very well the evolution of the landscape in these horizons or layers.
Then more sapric material. We have more older material because the process paludization.
Yeah. And so these horizons and layers, they spend only hundreds of years to produce a thin, shallow horizon, but to produce very thick and deep horizons, we need some 10,000s of years, when can spend some millions of years to produce a very thick O or H horizon. So accumulation of organic matter and production of organic layer also spends a lot of time, because of course we have the production and accumulation of the organic matter, but at the same time we have the decomposition of that material. And the paludization is faster than the reading, so the accumulation of organic matter in water areas and water logget areas and areas influenced by water table or by tidal water is faster than areas that we don't have too much water, so cold regions or even dry regions. The accumulation of organic matter, it's not faster than areas that you have the water logging conditions, that you have a lot of water. So the paludization is faster than littering, and the littering is slower than paludization, okay? This process is not limitless, because the formation of an organic horizon depends on the producing of the organic material, and we have the decomposition of the material, of course, the organic material, but also the plants couldn't survive in very thick organic layers. They need some minerals, they need mineral materials, because in general, these organic layers or horizons are very poor in nutrients. So in general, the plants need more nutrients and they need to explore the mineral horizons and layers. So if you have a very, very thick horizon, this could be a problem, and the accumulation of organic matter start to decrease, because the production of the organic matter start to decrease, because plants start to suffer with the lack of nutrients. Okay, and of course we can see some rates, accumulation rates here, like the rainforests. They produce less than 1 centimeter of year of organic layers, and flooded areas, they produce a high variated rate, varying between 0.3 and 1.6 centimeter per year. So you can produce a thicker organic layer in flooded areas by paludization than only littering in rainforests, because here in cold or oxidating environments, you have a high decomposition of this organic matter. And here, the decomposition of the organic matter, of the organic residues, are slower, because the microorganisms, they are not so faster, they are not so efficient to decompose organic matter in flooded conditions, in waterlogged conditions. And other processes that are very important to understand the evolution of soil is the desilication, the release of silicon by the weathering of primary minerals. So this process is quite important, because it's common to at least all soils that we can think. All soils, they are always losing silica by the weathering. We can only mention some exceptions, specific soils that don't release silicon, okay? But the majority of them are being weathering, and all of them are releasing or losing silica, okay? And we can see that these are quite related to content of easily weathered minerals. Of course, if you have higher content of pyroxene or feldspar, your material, the soil, will suffer the desilication faster. If you weathering a soil that have a lower content of these minerals, these primary minerals, the process is slower, okay? And of course, if you present highly resistant minerals like quartz, zircon, and other minerals, they will influence the rate of release of silicon because they are highly resistant minerals. They are very stable minerals, okay? And we can see some boundary between the soils that present and they didn't present easily weathered minerals, something like 100 of millions of years. They indicate a very good boundary between soils that present high activity clays with primary minerals and low activity clays with only highly resistance primary minerals. So this age, it's very good to distinguish between soils that you present a lot of feldspar, plagioclase, olivine, pyroxene, smectite, illite, and those are related to kaolinite, goethite, hematite, and quartz, essentially quartz in the same fraction. So the weathering of primary minerals is quite related to this age. Okay, several studies suggest this age like a very good boundary between these two groups of soils.
I remember we have a graphic, kind of graphic with colored bowing with the resistance of the minerals. That's okay?
Yeah. I don't like very much that series, the Bowen series, because it's not so simple. We need to understand that some minerals, they have other properties that influence its resistance to weathering, to be weathered, okay? But it's very good way to a general landscape, a general perspective of how mineral could be weathered and how fast it could be weathered. Okay?
Okay, teacher.
So now we finish the discussion about the soil formation factors, and we could start the discussion about how could we use some morphological descriptions to describe changes in the soil through time, okay? When we describe a modern soil, we usually describe several properties that compose, several properties that compose the morphology, like color. We usually describe color. Oh, the color of soil is 10R or 10R2/3. So it's very red and present low value and low chroma, or it's 10R and 6/8. So it's very red but present high value and high chroma. So they are very different horizons or soils. Okay, we usually describe the color of the material, and we describe color of models or concretions or nodules if we can register these bodies in soils. We also should describe the structure of the soil. So the structure is angular blocks, it's laminar, it's wedge, it's prismatic, it's columnar, because the structure, it's quite related to content of clay, the nature of the clay, and some processes that we can see in the field, like the high content of evapotranspiration, the activity of the clay, if our clay that has a lot of smectite and the light, or it's just a colonite clay or goethite, rich in goethite and hematite, they differ. And if you can register in that soil, in that horizon or layer, a high content of organic matter or a low content of organic matter, the structure tells us a lot about all these conditions. We also are always describing the consistency of the material in a dry condition, in wet condition, and in moist condition. So we describe, okay, how hard is the material to be broken, how friable is the material, and the plasticity and the thickness of the material. How could we describe this material, the resistance of the soil in different conditions that represent different water levels or water contents in soil. We also describe the presence of voids, presence and type of voids, the quantity of voids too. In roots, we always are describing voids and roots. We describe also the presence, if they are present, of course, of clay skins, how much could we describe and how easily could we found. Someone raised her hand. Oh, let me just know. Okay. Oh, please, Nadima. Open it.
Okay. JJ, can you hear me?
Yes, I can hear you.
Can animals form void, like microorganisms? Can they form void? Something like termites. Can they form void in a soil?
Mm-hmm. Yes, yes. Animals, roots, and at least materials that you don't have on biological activity. You also can identify voids there, like horizons or layers or even soils that present high content of clay and high activity clay. They could expand and they could contract, so they can change its volume according to the quantity of water, so you can produce some voids that are not related to biological activity. And we also can find some voids, some pores that are only related to weathering. I will show you a picture of some rocks or some sea horizons that you can find some voids that only are related to weathering. So in the past, you have a grain of feldspar, for example, and that grain was weathered, completely destroyed, and nothing formed in that place. All the material was destroyed, so you form a void inside the rock. Okay, so you can find some voids that are quite related to ants or dwarfs, termites, but you can find some roots influence information of voids too, but we can also find voids that are not related to biological activity. Okay?
Okay.
Okay. Let me go back. Here. Okay. So the voids are some properties that we usually describe. Oh, sorry. We usually describe some voids in each horizon or layer that we describe. We usually describe the clay skins when they are present in that horizon or that soil. We also describe stress features if they are present, okay? In the next class, we will discuss the difference between these both features, the clay skins and the stress features. They are quite different, but in the field, they are similar. So we need to use some tips to distinguish those, okay? Because it's quite important to distinguish them. And if we have in the field, we should describe the models, concretions or nodules, the presence of these materials in each horizon, the color of these materials in each horizon or each layer. Okay, so this is what we use to describe when we have a modern soil. But when we have an ancient soil, when we have a paleosol, when we have a buried soil, which morphology, which parameters, which properties should we describe? Basic, the same. We use the same properties to describe, but now we should understand that some of these properties are related to formation of that horizon that was produced by the pedogenesis that formed that horizon, and some of them could change after the formation of that soil. We'll discuss this in the next class, but some morphological properties could be changed by, for example, the burying of the soil. Soil was buried, so the absence of oxygen could change the pH of the horizon or the soil or the layer, and this could change the color of the soil because you change which minerals could be found in that horizon because you change the pH, the quantity of electrons that could be easily be changed there. So you can change from a red soil to a yellow soil, or the opposite. You can change from wet and yellow soil to a dry and red soil. So you can change the color after a burial process. So we need to understand that some morphological processes are quite related to the formation of that horizon, are quite related to formation of that soil, and some of them could change after the process of formation of that soil. Oh, JJ, how could we know that? Well, we need to make several measurements and descriptions to understand which are the original morphological properties that that horizon or that soil possess, and which one were changed after the formation of that soil. Okay, so it's not easy, but it's very important and interesting to describe these changes of the morphological process through time. Okay, so let's start with voids, with pores. We should describe what? We should describe the type of these voids, the color of these voids, the presence or absence of infillings and coatings of these voids, and of course the quantity. I forgot to include here the quantity of voids. How much voids could we identify in a void? Okay, we have different types of voids. The Brazilians are not used to describe the type of voids, but if you are used to soil taxonomy or if you are used to WRB system, you always describing the type of voids, and they are very important information that we should describe and we should register. Okay.
Teacher, the voids can be measured with physical analysis.
Could you repeat, please?
The voids can be measured with the physical analysis in soil?
Yes, yes. But
Yes,
now
okay.
we will describe how some voids, some information about these voids could be measured in the field. Okay, of course, we can improve its information with lab analysis, like the quantity of voids and the size of these voids. We can easily measure in the lab, and we couldn't at least very easily measure this in the field, but we have several soil properties about the voids that we should describe in the field. Okay?
Okay, teacher. Okay.
Okay. So let's start with the type of these voids. We can describe some vesicular voids. These vesicular voids are isolated voids that present this spherical or ovoid shape, okay? It seems like bubbles in the beer or water or in the soda, okay? They are cavities that present this specific shape. And let me show you some pictures about this. Oh, it's wonderful. I love this kind of voids. You can see here, and we have different sizes. And this photo, you can see several voids that present a ovoid or spherical shape. They are vesicular voids. And we also can see this in micromorphological thin sections like this. You can easily see here and here and here, like bubbles. And here, but here in this case, we have some material, this dark material that are in fillings, okay? And here, the photo cut up and the half, but we can see here, this vesicular voids. All of them, these are observed in the field, of course, and these voids are observed in microscope in the lab. Okay, and I want to ask you all, how do you think that we could create this kind of voids in soils? Or if you found a horizon or layer that present this type of void, what this type of void should means to you, what this could tell you, how this horizon or this layer could be formed. Which information could we gain, could we extract from this layer, only using the type of void that we can see?
For me, I think can mostly be seen in a semi-arid area, number one, formed by biological activities from the shape.
Okay, so let's make some notes. Dry conditions.
The presence of the termites, biological, yes. Activity, termites, ants. I think it is the approximated with biological activity, I think.
Mm-hmm, mm-hmm. Mm-hmm. Any more suggestion that how this kind or this type of void could be formed? No? Okay, I will, oh,
No, teacher. Only this.
okay, okay. Okay, we have a very good start because dry conditions is one of the conditions that we can measure this type of void. These two pictures, this one and this one, was taken in semi-arid regions. So the vesicular voids are related to dry conditions. So we can measure this kind of voids when we have a high evapotranspiration or higher than the precipitation, okay? But how this type of void could be formed in dry conditions? Let me show you. I need to draw this. Let me just add a new slide, so I think that will be easier. Okay, here. So there's the soil, okay. And here we have the A horizon, the B horizon, the C horizon, okay. And you have a dry climate. You have dry conditions. You have a kind of vegetation that is just a shrub or a basals. You don't have a dense vegetation cover, so you have a lot of soil that exposed to rain, okay, like this. All this region is just soil exposed, are not covered by litter or vegetation, okay? And when start to rain, generally in dry regions, the quantity of rain, it's very high in a low, and with a low duration. So the duration of the rain season and of the rain events, it's very short, but the quantity of water, it's very high. And the incidence of water in the soil surface start to break the pads, the aggregates in the surface. They start to break the pads because you can imagine here you have an aggregate in the surface of the soil, and here we have a raindrop. The raindrop, it's quite higher, and the velocity of this raindrop, it's high. So when the raindrop achieve this aggregate, it's just broke it. So it's very common in soils that we have a lot of soil exposed in the surface in dry conditions, that the horizon, the surface horizon, suffer the splash effect, the destruction
Teacher.
of the pads in the surface. What?
But these voids don't is destroyed for older process. This process is responsible for to how do you say maintain.
Oh, yes, yes.
Maintain.
I'm just a moment, and I will achieve that. Okay. Just for this moment, think that you start to break to destroy these pads, these aggregates in the surface, and you release a lot of clay. So in the dry climate, it's quite common at the surface horizon, you produce a lot of clay films in the surface because the aggregates, the pads, are always being broken or destroyed by rain. And if you didn't have a high slope, if the relief it's gentle or a plain slope, the water, the surface water is not so high. So the water migration in the surface is very calm. The clay start to deposit in the surface of the soil. The clay didn't move very fast or to a lot other area. So we start to create a thin layer of clay in the surface. And when start to rain again, let me just make this thin layer of clay. When start to rain again, the water drops also can broke this thin layer of clay and produce something like this. Let me just make a better draw about this. Let me just see this here so we can easily broke this thin layer of clay by the action of the water drops. You can broke this, something like this. You can create some voids, strange voids, some holes, because the impact of the water drop, okay? And this clayic thin layer get moist very easily and start to collapse and incorporate some bubbles of oxygen, because the action of the water drop, it's always changing the surface of this clay thin layer. So this material in the beginning are just a lot of thin layers of clay. After that, start to have some holes or an irregular surface because the water drops. But this material is moist, so they can easily change its shape. And if this material, let me try again, if this material that is irregular surface now are only with a stratum that's a parallel, because this material was again well distributed, the clay was distributed to produce a parallel surface, you can preserve some water bubbles or air bubbles inside this thin clay layer. And when this material gets dry, this water or oxygen bubble keep here, but only the shape that produced in the material, okay? So the vesicular voids, they are not related to biological activity. Termites and ants and other animals, they didn't produce this kind of void. They're only formed by physical chemical process, especially physical process. The rain drop that affect a thin clay layer in the surface and produce a layer that host some air bubbles or some water bubbles inside this clayic thin layer. Okay, and when it get dry, you just can see this shape, this bubble shape inside this clayic layer in the surface. So it's a kind of void that only is formed in the surface when we are discussing about a dry condition, a dry climate, okay? Because it's formed by the splash effect. This splash effect produces a thin clay layer that hosts air bubbles and water bubbles inside this layer. Everyone could understand this process?
Yes.
Yes. Yes.
Oh,
Yes.
okay.
Yes.
Okay. This is only one type that we could produce vesicular voids. But we also can see vesicular voids in other kinds of environments, like this thin section. It's a thin section of a soil that's formed in waterlogged conditions. So if you have a soil and the water table is here, so the water table level is here, and all these horizons and layers, they could be below the water table in the wet season, and here is the water table level in the dry season. So we have some times that all the voids are fulfilled by water, and we have some seasons that we have oxygen penetrating inside the soil.
Hi.
I think that someone forgot the microphone open. Just a moment. Okay,
Sorry.
no problem. Okay. So if you have a horizon that sometimes it's under the water table level and sometimes above this water table levels, you can produce some bubbles inside this horizon or layer. These bubbles are formed by water or oxygen, air, atmosphere that could be locked inside a void and produce this spherical or ovoid shape. Okay, this type of voids are only formed in high activity clays. So if you found vesicular voids, they could be related to an area that it's seasonally flooded or not. So they could be related to a subsurface horizon or a surface horizon, but they always are related to high activity clays, because this shape that's needed, this spherical shape, it's only formed by the compression of air or water against the solid particles, the clay particles. And if you have a low activity clay, you can't produce this shape. But if you have a high activity clay, they are very plastic and sticky, this clay could be modeled, they can reproduce this shape, this ovoid or this spherical shape of the bubble, okay? So we can see vesicular voids in the surface of some horizons when we have dry conditions, and we can find also some vesicular voids in subsurface horizons when these voids are related to the water table oscillation, when we have horizons that could be below or above the water table level depending on the season, okay? In both cases, we need high activity clays to form this shape of void, okay? So it's quite interesting that only basic information like the type of the void could tell us if that horizon was formed in a dry climate or a waterlogged condition. Of course, we need to understand other properties to know, okay, this was a soil produced in the surface in dry conditions because the color is red and I have a lot of iron, or this horizon was produced in a subsurface horizon influenced by the water logging, and because we have a gray color, we don't have a lot of iron, so the conditions are different, and I can understand very well the formation of each horizons, okay? So the type of void, it's a very good information that we can use, but we need other morphological evidences, other morphological properties to fulfill the story, to understand better the evolution and the formation of that horizon, okay?
Okay.
Everyone understand very well the formation of this voids?
Yes, I understand.
Okay, okay. We'll finish our class now, and the next week we will continue to describe some types, some shapes of voids, and it's very important because each shape helps us a lot to understand some process, some specific process, okay? So I will share with you all some material, some reference that you should read, and will help us to discuss this process, okay?
Teacher, I have a doubt. These voids can be this void is possible to see in a morphological analysis?
Micromorphological and in the field. You can see
Okay.
with your eyes, yes, like this pictures. Let me show you again. Just a moment. There's two pictures. Okay, or these two pictures, this one and this one are field pictures. Like you can see my fingers here. And this picture was captured by a microscope. So you can see some voids in the field, and you can also measure them in the lab.
Okay.
Keep my pen.
Okay. Okay, teacher.
Okay.
Thanks.
Welcome, welcome. Any doubt? It's okay?
No, that's okay,
No?
teacher.
Okay, okay. So see you next week. And if you have any doubt, just send me a mail, okay?
Okay,
Bye-bye.
teacher.
See you.
Bye-bye.
Bye-bye,
Bye,
guys.
Bye-bye, guys.
Bye, guys.